9.6 is and 9.7 is a section we're covering today. There's just a look at the schedule I just described. As you can see, today we have the quiz. Oh, these days are off, but anyways, we have a quiz next time test, and we start a project. So 9.6, identify symmetry. A line of symmetry occurs in a figure in a plane if the figure can be mapped onto itself by reflection in a line. Line of symmetry is associated with a reflection. A line of symmetry is a line that maps a figure onto itself. Rotational symmetry. Rotational symmetry is a figure that can be mapped onto itself by a rotation of 180 degrees or less about the center of the figure. So a rotation, you rotate it about the center of the figure. How many lines of symmetry does this hexagon have? So where could we draw a line so that it would reflect onto itself? How many times could we do that? Somebody have an idea? This is not a regular hexagon. Okay, it's two of the sides are longer than the others. The answer would be different if it were a regular hexagon. All right, the lines of symmetry we have here are, there's one, right? If I folded this onto that, everything would match up. Okay, you can kind of think of it, like if you folded something, you fold it over the line, the one side matches the other side. And then, can anybody think now that I've drawn one? Can anybody describe where another one would be? Faith?
Horizontal.
Yeah, a horizontal. So we could have one there, and then I would say those are the only two on that figure, assuming it's not regular. Yeah. So it's those two lines of symmetry. Okay, what about, now we have a regular hexagon. How many lines of symmetry does it have? Okay. He says 3. Okay. Anybody have another answer? Yeah. Yes, it actually has 6 because I can not only draw lines of symmetry that cut the sides in half, like these. Right, each side is cut in half. There's 3, and then we could have some that go through the angles, right? Here, here, and here, right? So it actually has 6 lines of symmetry, dividing the sides in half, and then 3 lines dividing the angles in half. Looks like that. All right, let's take a look at this figure. How many lines of symmetry does it have? Gunnar, what do you think? 1. I agree. 1 line of symmetry looks like that. All right, everybody have the idea with lines of symmetry? All right. Here's a different one. How many lines of symmetry does this figure have? What do you think, Devin? Okay, there's more than 2. Anybody else? Logan, what do you think? What? I think she's right. I think it's 6. 8. All right, let's see. Let's draw them. So we've got this one, that line, there's 2, then we've got 3, and we've got 4. Okay, there's 4, and then I think it would take, we'd have 5, 6, 7, 8 lines of symmetry. There are 8 lines of symmetry in that petal. So you fold along the gaps between the petals, and then you fold along the center of the petal, and you have your lines of symmetry. All right. How about the starfish? How many lines of symmetry do you think it has, Jacob? Let's see. We've got one here, one here, and one here. So there's 3. I don't think anybody see any more? I think those are the 3 they have. I would say 3. And it says 5. All right, let's draw it again. So we've got one here, one here, one here. Oh, then we have, I guess, for each point through each point of the starfish, then we would have one here, and we would have one there. So there's 5 lines of symmetry. Yeah, for the sheep, there's 1 right down the middle, right? Right there. All right. Draw a hexagon with no lines of symmetry. Go ahead and attempt to do that, and then I'll put a figure up on the screen. Hexagon, that's a 6-sided figure, no lines of symmetry. So obviously it can't be regular. All right, could look something like that. None of the lines are the same length in this hexagon. All right. Does the figure have rotational symmetry? If so, decide how many, if any, rotations that map the figure onto itself. All right, so we have this parallelogram. So we wrap, if we put a point in the center of the parallelogram, can I turn, like take this point here on the parallelogram, can I turn that parallelogram or rotate it? We're just going to assume we rotate counterclockwise, so it's positive rotation. Can I rotate it so that that figure maps onto itself besides rotating it all the way around, 360 degrees all the way around, so that point ends up where it was before? Is there a rotation that I can rotate that to map the figure onto itself? If so, how many degrees?
180.
Yes, 180 degree rotation. I could take this and I could take it around to here, and it would map onto itself. So this has one rotational symmetry, 180 degrees. Octagon. Okay, what rotation? What's the smallest rotation I could make on this to map it onto itself? If it's an octagon. So let's think about that. So I want to take, if I want to rotate this, we're assuming this is regular. All the angles and all the sides are the same. If I want to take this, let's say this point here on this vertex, if I want to take this point and I want it to move to here, to there, right? How many degrees would I have to rotate it?
Would it be 45?
How'd you get that?
360 divided by 8?
Yeah, we'd take 360 and we would divide it by 8. It would be a 45-degree rotation because that we're just turning it, like turning it just, a 45-degree return. Then I could keep turning it 45 degrees 8 times, and then I would end up back at the beginning. But so the rotation on this, it had a rotation of 45, 90, 135, or 180. They all map the octagon onto itself. I would go on to say that it has 225, all increments of 45. So if I ask you what the rotation is, the rotational symmetry, just name. You can just if it's like this octagon, it has the 8 rotations. Name the smallest degree. Say its rotational symmetry is 45 degrees. You don't have to list all 8. Trapezoid. Does this have a rotational symmetry less than 360? What do you think, Aaron? No, it does not. The only way you can rotate this is 360 degrees. There's none of 180 or less. All right, does this rhombus have rotational symmetry? Eric, what do you think about the rhombus? Does it have rotational symmetry? And if so, how many degrees?
Yeah.
90 would take this point up to here, right? It's not 90.
180.
180, yeah. It'd be 180. You have to go rotate it from here around to there. 180. And it's about the center. What would be the rotational symmetries of this octagon? Gauge. How many degrees?
180.
That's one of them, but that's not the smallest one. We want to name the smallest one. Yes, Faith. 90, right. Because when I take this point to here, if I measured the angle from the center, that would be a 90 degrees, right? So it's it has a 90, the rotational symmetry on that is 90 degrees. Let's see here. Yes, on the quiz, I just asked you for the smallest number, so you don't need to list all of them. Like, you could say this has a 90-degree rotation, has a 180-degree rotation, 270. All you need to do is name the smallest one. Right triangle. Does this have rotational symmetry? Seth? 180 would make it look like, if we rotated it at 180, it would look like this. Is that rotational symmetry? No. It doesn't. There's no rotational symmetry on this. There has to be something the same in the figure, right, for it to be rotational symmetry. None of these sides are the same length, so there's no way it could have rotational symmetry. All right, so identify the line of symmetry and rotation symmetry of the equilateral triangle. Which one do you think it is? What do you think, Brandon?
3 lines.
Okay, 3 lines is correct. What would be the degree rotation? There's 3 vertices, so yeah, get Abby. What?
120.
Yeah, it's 120. I take this point from here to here. That's a 120-degree rotation. All right. 9-7. Identify and perform dilations. Okay. What do we typically think of when we think of dilating or dilation? What do you think of? When do people talk about dilating? Their eyes, right? You get your eyes dilated at the eye doctor, right? It's keeping its shape. It's just becoming bigger, larger around, right? So a dilation is a transformation that stretches or shrinks a figure to create a similar figure. Dilation. The center of dilation is the fixed point. Right? It's a fixed point, center of dilation. Scale factor of a dilation is the ratio of a side length of the image to the corresponding side length of the original figure. All right, so your scale factor, you're going to put the size of the new figure over the size of the original. All right, the original always goes on the bottom. It's easy to confuse. Just remember your original size goes on the bottom. The prime size, this number could be smaller than this, or if the figure gets smaller, or it could be bigger than that if the figure gets larger. All right? So in a dilation, CP prime, so that's the figure after it's dilated, is 3, and CP is 12. Tell whether the dilation is a reduction or enlargement, and find its scale factor. Okay, so what do you think it is? The prime is 3, the original is 12. Would that be a reduction or an enlargement? Kayla. Goes from 3 to 12. How many goes from 12 to 3? It's a reduction, and the scale factor, okay, is the number that it ends up at goes on top, so it would be 3 over 12, and we're going to reduce that fraction. 3/12 reduces to what? Logan? 1/4. Nope, went too fast there. So yes, it is a reduction. The scale factor is 1/4. Any questions? All right. Here, find the scale factor of dilation, then tell whether dilation is a reduction or enlargement. So we start out with this shape at P, and it goes to P prime. Enlargement or reduction? Carly? Enlargement. What do you think the scale factor would be?
8 or 12 or
Very good. It's 12 over 8, which we always are going to reduce the fraction. 12 over 8. 4 goes into both of those, would be 3 over 2. P prime is an enlargement. Any questions there? All right. Reduction or enlargement? In this example, what do you think? Anybody? What do you think? Somebody? Was this?
Reduction.
It's reduction. What would our scale factor be?
9 over 15.
How'd you get that?
It was originally 18 over 30.
Yeah,
but okay.
18 over 30. It's a reduction. We can reduce it even further than from 9 to 15. Okay. What goes into both? What's the largest number that goes to both into 18 and 30? 6, right. 6, so we could reduce it. 6 goes into 18 3 times and 35. So it's a reduction, and the scale factor is 3 to 5. All right, now, it says draw labels DGF, then construct a dilation of DEFG with point D as the center of dilation and a scale factor of 2. So how you're going to do this, we take the original figure. I think you have it in your notes, right? And if D is the center of dilation, then you're going to lengthen the lines along from D. So I draw these lines through each side, or through each point from D. I draw these lines out, and then it's a scale factor of 2, so everything's going to be 2 times longer. So I'm going to measure the distance DG. Okay, say for example it's 2 inches. Then I double that, because the scale factor is 2, so I multiply it times the scale factor, whatever that measurement is. I multiply it times the scale factor times 2. So my new point, G prime, is going to be twice the distance. So we put a mark with our compass, mark that arc, you measure this, then mark it. I take my compass, measure it, mark it. I do that with each line. DF, I double it. There'd be and then I double DE. And then I call this G prime, F prime, and E prime. And we can draw the new shape. Looks like that. Okay? So they did the same thing I did there, right? You double, multiply times the scale factor, and you get your answer. Okay. Any questions on that? Okay, so the next example, you've got triangle RST, right? Construct a dilation of RST with R as the center of dilation and a scale factor of 3. Go ahead and do that on your own. Okay? Do that on your own. You'll need your ruler. or your your compass to measure the length, but the ruler to use this to draw the straight line. Go ahead and dilate that figure by a factor of 3 with R as the center of dilation. Yes? Mm-hmm. Okay, from R, you draw lines out. Draw a line from R. Lengthen that line, lengthen that line. You don't have to measure it. Just draw a line. Okay, and then draw one the other way. Keep going, keep going. There you go. All right, now measure the distance of RS here, and then duplicate that distance twice. So you measure this arc, measure it again. There, I've lengthened it by 3. Do the same thing with T. Okay, you show your arc marks. Okay, this is like a construction, so you need to show your arc marks. You draw a line from R through S and R and T, and then you measure 3 distances. Draw lines like that and like that. Measure that, mark it twice. See what you got there.
I screwed it up.
Yeah. You did a translation. No, there's no point there. You don't need to draw that one. There's no. You only go. The only thing you're going to move is the point S and T. So you just measure that, mark it twice. That's your new point. Taking pictures?
Mm-hmm.
All right, that's right. Then you got your compass. The compass, so you're going to measure. If you didn't have your compass, then I guess use your ruler. It's not a construction if you do that, but then you measure this distance RS twice. Mark it here and here, and then that makes it 3 times as long. All right, so what this should look like is, so we extend from R. We extend the line through S, on out, and through T, on out. And then I'm going to take my compass, I measure this distance, and then I keep my compass the same. I make an arc here, then I move it, I make it here. All right? RT. I've got the distance, I mark it again. All right? So we have the new shape. Any questions on that? No questions. All right. So like I said, we have a quiz over these 2 sections next time. Now one thing I want to go over again on when we're talking about rotation, I don't think I said this, but if it is a regular shape, let's say it's a regular hexagon, right? And they ask for the angle of rotation, you're just going to take 360 and divide it by the number of sides. If it's regular. So this would be 360 divided by 6 to have a 60-degree rotation. Okay. Any questions?